So, okay, welcome back to MOVID 20. Well, to the afternoon session. Now we have with us Maria Yakerson, which is going to talk about motivic generalized cohomology theories from the frame perspective.
Thank you very much for self-invitation. I'm very happy to see all of you. And yeah, I'll just remind that we made these talks longer so that you can ask questions during the talk. Denis, did you remind how to do this? No? Okay, so if some people are new in the afternoon session, I'll remind that you are welcome to raise hands, which you can do on Zoom by pressing participants, and there is a button raise hand. Then you can either unmute yourself and ask a question, or Denis unmutes you. Or write in the chat. I mean, feel free to ask questions. Okay, so the previous speakers have set a very high bar. So because of that, I'll give a different kind of a talk. Today in the morning session, we heard a bunch of interesting proofs, and I am, on the other hand, not going to prove anything at all. I'd rather give an overview of the subject we've been studying for the last 3 years already. And by now, I think we have not only some general picture, but also we have an idea of how the main cohomology theories of interest fit that picture. So I would like to give a big overview of what we have understood. So I will talk about combined story coming from several projects, and most of the statements are from joint work with Elden Elmanto, Marc Hoyois, Adeel Khan, and Vladimir Sosnilo. And one result is also joint with Tom Bachmann. And there will be also mentioned joint work with Marc and Joachim Jelisiejew and Denis Nardin. Okay, so let's start. So the main goal of motivic homotopy theory is to work with generalized cohomology theories for schemes, in particular smooth schemes. So we do this. So we study generalized cohomology theories for well, smooth, or mainly smooth, but not necessarily smooth schemes over some base. Let's call it S. And main examples are maybe motivic stable homotopy groups, which encode information about classical stable homotopy groups, if you do this over S being complex numbers. So this is one example. Then another important example is algebraic K theory for smooth schemes, or like homotopy invariant K theory in general. So algebraic K theory. We also care a lot about algebraic cobordism, which is another very interesting cohomology theory, and other examples. And so the main idea for today is that although all these cohomology theories are of course contravariant, but so they all have, okay, how do you speak and write at the same time? That's not so easy. So as cohomology theories, they're all contravariant, but there is additional covariance. But there's also intrinsic covariance along some special kind of maps, some maps of schemes. And so the main idea is that if you take this covariance into account, then you will get new models of the interesting cohomology theories, and some relations between these cohomology theories will be more well understood. So if you take this covariance into account, get new models for interesting cohomology theories and relations between them. Okay, so this was a moral in words. So the plan of the talk is that I want to give some general setup, which may look abstract, but then the main point is to actually give examples, so demonstrate how it works for concrete cohomology theories. And at the end, regarding of how much time I have left, I will give some application. Okay, good. So, okay. So the first, I want to explain this general setup. And for this, I'd like to talk about framed transfers. Okay, so to do this, I need to recall what is the stable homotopy category. And well, luckily, I'm not the first speaker, so you have already heard today some things about unstable and stable Motivic homotopy category. I will remind some things we need. So in general, SH of S is, well, informally speaking, it's a home for cohomology theories on smooth schemes over the base scheme S, which satisfy homotopy invariance, which in our settings is A1 invariance, so making a fine line contractible. A1 invariance. Some kind of descent, which is so-called Jelisiejew descent. Jelisiejew descent, and a tier duality. So some duality which you have seen different instances of in different cohomology theories, which allows to actually compute something sometimes seldomly. Okay, so precise definition is that SH of S is defined as P1 spectra in A1 invariant Jelisiejew sheaves on smooth schemes over S. And I will use this construction later once again, so I will denote this story as star. Okay, so Marc used in his talk the notation for the global section of a Motivic spectrum. So I will use another version of this construction. So associated to a Motivic spectrum, you can consider its cohomology space. So I would like to take also the mapping space from the unit object to, sorry, that's X, to this cohomology theory on X, but I would like it to be a space. Marc took the spectrum. And so as I said before, this since we deal with cohomology theories, this is contravariant with respect to maps of schemes. Question, so the main question which leads to this whole set of studies is which covariance does this cohomology space have? Okay, and so the first example of covariance it has is, so as a cohomology theory, it has addition. So addition gives you a map from e of x times e of x to e of x for any x. But you can think of the source as the value of your cohomology theory on the disjoint union of two copies of e of x, and then you can think of this as a covariance along fold maps. So so this you have like so covariance and like the wrong way maps are called push forwards, or I'll call them transfers. So you have like transfers along fold maps, and well, you also have them for not just two fold maps, but like more copies of disjoint union of x, and this way this transfer maps encode the addition, which is commutative and associative up to higher homotopes. So this transfers, if you look at them coherently, so like if you take higher coherence into account, encode that addition is commutative and associative up to higher homotopes. I mean, it encodes this whole set of data. So okay, but there's more to that. So this you also have classically in topology. And okay, so the general natural way to generalize fold maps in algebraic geometric settings is to consider finite total maps. So more generally, if you have a finite total map of schemes, so I don't necessarily need these schemes to be smooth. Actually, yeah, I should have said. So the definition makes sense for X being any scheme. Okay, so if you have a finite total map, then it will induce transfer map on your cohomology theory, and this follows just from a T duality. So it's actually maybe a good way to think about T duality. And so more generally, if you have F not necessarily finite total, but let's say a proper smooth map, so relative dimension is not necessarily 0, then you will have a generalization of this transfer map. It will be twisted transfer, so you must twist the source with the relative cotangent sheaf. So okay, one sec. So this is so this twisted cohomology space is a generalization of the cohomology space I've just defined. It's like you look at the mapping space from the Tom spectrum on your relative cotangent sheaf. And so you have this generalized push forward or transfer map, which if you're in a tall map, then this sheaf is just 0, so you get what we just had before. And actually, this is a more general version of what Tom was speaking today in the first talk. So Tom was telling you that if you have a monogenic field extension, then so finite monogenic field extension, then you have transfer maps on those strictly homotopy invariant sheaves. And if you choose the generator, then you get like well-defined transfer map. But if you don't choose a generator of the field extension, then you will get these twisted transfers, and the twist will be the relative canonical sheaf. So this is exactly, so what Tom was telling is an example of this functoriality. But the interesting part is that there is a more general story, as in if your map is finite local complete intersection, which I write as LCI, which means that you locally can factor is as regular immersion followed by a smooth map. Then you can, okay, so this LCI condition makes sure of the fact that your relative cotangent complex is a perfect complex. So it gives you a class in the K-theory space of Y. And that's actually very good for us because the definition of the twisted cohomology space makes sense. Yeah, maybe I should have said what is the Tom spectrum. So sorry, the Tom spectrum is like the, oh, okay, let me tell you what Tom space is. So Tom space for a vector bundle in algebra geometric settings is just is the quotient sheaf where you quotient out by the zero section, sorry, by the complement of the zero section, and so you can build a spectrum out of it. And okay, so the construction of the twisted cohomology space also makes sense not just for vector bundles but for all K-theory classes. So you can you can make sense of twisting with this relative cotangent complex, not the sheaf as before. And you also have the push, so like this twisted kind of push forwards or transfer maps. Okay, so this is a generalization of the previous construction, and okay, that's much better because many things are LCI but not smooth. And this means that that for every cohomology theory, for every spectrum, this cohomology space has transfers, like push forwards, along finite LCI maps with given trivialization of this relative cotangent complex. Okay, and also under these conditions, F is also flat. So, and so it's flat and LCI. This is called symptomic. So flat.
So, sorry, can I ask you, so are you saying that if you have a trivial cotangent complex, like a cotangent complex with trivial K-theory class, then it's automatically flat?
No, I'm saying that if you have a finite LCI map with this extra condition, then you're necessarily flat.
Necessarily flat, okay, thank you.
Okay, so I'll give examples in 30 seconds. I just wanted to say that, so we have transfers along finite symptomic maps with the given data of trivialization, which we call framing because it's a generalization, like it's an analog of framing in topology where people look at like framed cobordism and stuff like that. Framing. So let's do this framing. And we call this framed transfers. Framed transfers. So examples of like cohomology theories having these kind of transfers. For example, if you think about Chow groups are contravariant, but they have proper push forwards. So, and okay, so they have proper push forward, which shifts the degree. And if we want the degree to be the same, then these are finite push forwards. So I have proper push forwards.
Yeah. There's a question in the chat from Tony Anala. Can you also get transfers along proper SEI maps?
I think so. So the actual condition that, oh, I forgot to say whose work is it? I'm so sorry. So this construction is due to Denis, Jin, and Adeel Khan. And the actual condition they required in the first paper was smoothability, which means that you have not local factorization of like in the LCI definition, but a global factorization into regular immersion and followed by a smooth map. But as far as I know, they, or actually you, Marc, also, managed to avoid this condition, which will appear in the future paper. So then it would work for proper maps too, right? As far as I'm aware, it works, but it's not written down yet. Okay, so I was saying that an example is like Chow groups having proper push forward or finite if you don't want a shift in degrees. Or for example, K-theory, it doesn't have push forwards along all proper maps, but so K-theory would have transfers along finite flat maps. So, but okay, you may be suspicious until now, especially if you didn't listen to Tom's talk carefully, because these examples don't need the help of the trivialization. So I usually think of like this trivialization is like some extra help for your cohomology theory to have push forwards, and some cohomology theories don't need this kind of help. They're oriented, but some others do need. So like this, so like, so emission K theory, for example. I don't want to write precisely which kind of transfers it has, but like it does need framing for transfers. So like these two examples didn't need framing. Need framings. Okay, are there questions? Okay, so it turns out that not only this functoriality exists.
There is a question by Shahar.
So this vanishing of the relative tangent complex, is it as a property, or do you actually need a trivialization for the transfer?
It is a property. So yeah, thanks for asking. So under these conditions, if you have a finite map which is local complete intersection, your cotangent complex does not have to be necessarily trivial in K-theory, or there can be different trivializations. So it is extra data. Sorry, I meant to say it is like extra data.
Okay, thank you.
Yeah, okay. So, okay. So the main moral until now is that there exists this extra covariance, and the first main statement I want to make is that if you encode this data of push forwards coherently, then there is also uniqueness. So not only this covariance exists, but it's unique if you encode it correctly. So, so it turns out coherent frame transfers are are unique for each generalized cohomology theory, for each Motivic spectrum. And okay, that's an imprecise statement. Let me tell you a precise statement. So the first theorem I want to formulate, which I want to use later to give examples. So okay, so so this is due to us and over a perfect field, and then Marc generalized it, but it's a very deep result. It's so this whole story started with Voevodsky's idea about framed correspondences and framed transfers, and later this was his ideas were explored and made work. Okay, my English is not very well, not very good. By St. Petersburg School, so Garkusha, Panin, Ananievsky, Druzhinin, and Neshetov. If you don't mind, I will not write all these names, but so uses hard work of Voevodsky, and let me abbreviate Ananievsky, Druzhinin, Garkusha, Neshetov, Panin. Okay, so okay, so yeah, the statement is this formulating this uniqueness in precisely in that Motivic stable homotopy category is equivalent to the framed Motivic stable homotopy category, where right-hand side is where you encode this covariant functoriality. So let me see what it is. Right-hand side is taking this P1 spectra on A1 invariant Misnevid sheaves, which I denoted like this, on the infinity category of framed correspondences where, okay, so where I want to encode this covariance. So objects are smooth schemes. So like in this category. So okay, so objects of this infinity category are smooth schemes, and a map from, let's say, x to y is given by a span sorry. Okay, is given by a span where this is any scheme, and the left leg is satisfies the condition which we want to have push forwards along. So it's like finite symptomic, and you're given the data of the trivialization of its quaternion complex. Okay, so this is just the precise formulation of the fact that this frame transfers are unique if you encode them coherently. And the main point of the whole talk is that although so moral, is that although the right-hand side in this equivalence is harder to construct than the left-hand side, right? So instead of smooth schemes, we take some like crazy infinity category. But the equivalence of the interesting cohomology theories on the right-hand side have, in a sense, easier presentations than in the left-hand side, which people are used to. So all the right-hand side is harder to construct. The equivalence of objects of interest from left-hand side are, in a sense, easier or more natural. Let me write all this.
Yeah, if you finish making it, there are a couple of questions afterwards.
Great, sorry. In the right-hand side.
Okay.
Okay, great. So this was the end of the general setup, and yes, please ask more.
So let me start with Ran Azuri.
Hi. Yeah. So why does this theorem that you just up there? Why, or in what sense that it means that coherent, the frame transfers are unique, or if you can just.
So this theorem tells, okay, maybe that's my interpretation, but it tells you that if you encode, like, so on the left-hand side, you just have usual cohomology theories. On the right-hand side, you encode from the beginning, like in the construction, this covariance. And this equivalence tells you that you don't get anything new, right? So that's how I read it. Okay.
I mean, maybe one helpful way of looking at this is to say that the functor from right to left is just forgetting the transfers, right?
Yes, you're right. Sorry. So yeah, there is an adjunction like from left to right is like create free transfers, from right to left is forget transfers. Okay, I won't write it. Rana, you're happy? Okay, so yeah, forget the functor which forgets transfers is an equivalence. Good.
Okay, so other questions from Christian Dalhausen, I believe the name is Kat. Is the null homotopy is part of the data so that the category is not discrete?
Yes, that's the issue. So it's an infinity, it's an infinity category exactly because of this K-theory trivialization, which like makes it not even an n category for any n, because K-theory space is not truncated in general.
And okay, is this a good enough answer? This came and this is not a question for you. This is a question for, yeah, thank you, satisfied. Okay, and last question from Toma. So and let him talk. Yeah.
So, so in particular, implicit in this definition on the right is that you have an Isnevich topology on spans.
Yeah, you're right. I must have said that. Yeah, I have a functor from schemes to, so like graph functor from smooth schemes to this infinity category. It just sends the morphism of schemes to a span where a left leg is equality. So it makes sense to speak about Nisnevich sheaves on this infinity.
So your notion of like everything about the Nisnevich topology comes from those kinds of morphisms. You don't consider coverings by things which are not graphs.
No.
Okay.
We mean that it's an Nisnevich sheaf and you restrict to smooth schemes via graph functor.
Thanks.
Okay. More questions?
This seems to be all. I don't know if anyone wants to ask something else. Nothing seems to be appearing. So, well, you can go on and I'll interrupt you like in 3 seconds when people figure out.
Okay, good. Okay, so examples of cohomology theories. We got to the main point of my talk. So I would like to maybe later to learn how to draw straight lines in this app. But before, take examples of Motivic space with frame transfers. And see which cohomology theory we get if we just apply frame suspension, infinite suspension functor to it. So cohomology theories in, so corresponding cohomology theories in frame settings, but we want to use that it's the same equivalent category, so it doesn't matter. Okay. So the first example, which has the most complicated construction, but the most obvious transfers, is that, okay, I can take, oh, by the way, there will all be some kinds of moduli stacks. Moduli. Okay, so the thing which first comes to your mind, if you're lazy, so if you don't want to put any work into construction transfers, is to consider the presheaf, which sends a scheme just to all finite symptomic schemes with this data of framing over it, so that like you would have obvious push forwards by just post-composing. So like this kind, we denote it like as finite symptomic frames, which is a presheaf of infinity groupoids, which sends a scheme to just finite, let me abbreviate it as finite symptomic U schemes with framing. So those which have this data for framing. So okay, when I write just presheaves on the left-hand side, you clearly can apply localization to them to make them even invariant sheaves, whatever. So and then the corresponding cohomology theory will be, okay, I can take frame suspension functor on it, but okay, this is something scary, but if you listen carefully until now and you remember the equivalence, you must guess that, okay, this is a unit in the, unit in the framed stable homotopy category, so it must correspond to the unit in the classical stable homotopy category. So that's no surprise yet. So we have some presentation for the, some kind of scary presentation for the Motivic sphere spectrum, but it's gonna get better now. You will see why I'm doing this, because okay, so we are now gonna simplify this moduli stacks to get more interesting examples. So let's forget about the framing and just look at finite symptomic schemes with no framing. So just a presheaf of usual groupoids, one groupoids, which sends a scheme to the groupoid of finite symptomic schemes over it. So groupoid of finite symptomic schemes. Okay, that's something nice. And we can also, so it also obviously has frame transfers, but just like ignore the trivialization, you're good. And okay, you may ask, so who is the corresponding cohomology theory in the classical stable homotopy category? And the answer is very nice, because it's actually, so you can guess if you think of this the following way. If you think that like this must be the universal cohomology theory, which does not need the help of trivialization. So the universal oriented cohomology theory. And the universal oriented cohomology theory is algebraic cobordism, as classically it would be complex cobordism. So this is algebraic cobordism. And the map, so the unit map of algebraic cobordism corresponds to just forgetful map, like forget framing map. So forget, I mean the induced map by the map on moduli. Okay, that's good enough. So that's okay. So all I'm making this collection of our results in one table, but like actually each of them is very much non-trivial. So this is due to us. Well, this okay. The above thing was from the theorem I mentioned before. Okay, and then but let's go on. So what would you do next? Well, maybe you can weaken some conditions. Turns out it's makes sense to forget about the LCI condition and just consider the stack of finite flat schemes. So same thing where you take finite flat. So there will be again a forgetful map because you can just forget this condition. And you may ask who is on the right-hand side, and I will not tell you yet. Let's move on to the next example, and then I will tell you who it was. So let's keep it as a secret for now, because the even simpler thing to do is to just take the moduli stack of vector bundles. So I mean the pre-sheaf of one group product, again, sure, each scheme takes the group product of vector bundles over it. And again, you have the forgetful map from finite flat schemes to vector bundles, which just forgets the algebra structure. So and okay, so this is forget algebra structure. And okay, so this guy actually is something familiar, at least when S is smooth over a field. Then this is the very effective K-theory spectrum. So, okay. Well, okay, you may have expected it because K-theory is something you built out of vector bundles, so this makes sense. But the maybe surprising thing is that it also gives you an answer for the question mark, because this vertical map, which was induced by the forget algebra structure, induces an equivalence on the spectra on cohomology theory. So it turns out that this guy is an equivalence. So the question mark is then also an equivalence. And this is due to, okay, so this is joint work with, what was it? Joachim and Marc and Denis. Okay, so, and then maybe the last example in this series is that the easiest moduli stack to construct is the constant sheaf. Say, I mean, you can take any abelian group, but let's just take integers. So you clearly have, again, frame transfers by just like forgetting the trivialization and just like having like usual finite flat push forwards as you do the like the stupid simplified constructions for Char groups. So, and then the corresponding thing. And so you have the forgetful, well, again, the forgetful map, which is just take degree of the vector bundle. And what you get is the Motivic cohomology spectrum. And okay, I'm writing it over arbitrary base. So actually that's due to Marc. And by right-hand side, I mean Spitzweg's construction of Motivic cohomology, which is like the spectrum which satisfies pullback. So this is Spitzweg.
Sorry, there is another question by Toma.
Yes, please.
Okay.
So I actually have two questions. So one is, if you take instead of vector bundles some kind of a quadratic, vector bundle with a quadratic form, would you get some form of Hermitian K-theory?
Yes, you get the very effective cover of the Hermitian K-theory spectrum. And I hope you can stay longer, because Denis will hopefully explain in his talk what will replace the stack of finite flat schemes in the Hermitian case, because it's not obvious.
Okay, yeah, that's very interesting. I have another question, and it's actually a little bit like it's about your previous theorem about SHS is the same as SHS frame that you had before. So, right. So if I'm looking at those kinds of functors, this kind of shift that you present, unless I'm confused, right? If you have like if you just take something like a product of x and x and you play with it, you get that even if you take shifts in spaces, they already have some kind of additive structure, right? Like a shift in spaces it can't be arbitrary. It's going to be at least an infinity space or something like that, right? So is there a way to say something like that instead of taking SH frame S as you defined, you kind of take a little bit less structure, like you don't take it in P1 stable things, but rather you kind of weaken it a little bit and still get an equivalence? Because you kind of get part of the stabilization for free.
So I think if you would have taken not finite framed transfers, but proper framed transfers, then as Tom taught me, you would, no, that's not specific. As Tom taught me, and now looks unhappy about it, you do get P1 stability for free, so you don't have to stabilize. But in this setting, you do have to stabilize.
Maybe I can say something that I don't know. That think about this might suggest what the correct answer is. So think about the case of spans, just of finite sets. If you take sheaves of spaces over that thing, you don't get all spectra. You get only connective spectra, right? And you need to add a group-like condition.
Yeah.
And here, if I recall correctly, I mean, Maria will presumably say, but I think what you get if you add a group-like condition and you take sheaves of spaces over this category of correspondences, what you get is a very effective spectra.
I don't think Tomer was asking about Motivic recognition. Okay.
No, I know that's a very good answer to my question actually. So if you're taking some kind of a group-like condition on the shifts of spaces, you're saying you're going to get a full subcategory of the SHS, but it's not going to be the entire thing because you need to you only get very effective.
That, for example, is the reason why you get connective very effective K-theory. Sorry. Here.
Yes.
I see. Okay. No, that's a very satisfying answer. Thanks.
Okay, I was about to say it in 5 minutes. Yes, Tom.
Oh, I mean, be careful that the base has to be a perfect field for this.
Yeah. Yes, I will say this. Come on, people, don't tell my talk.
Sorry.
It's okay. Just kidding. So, but since Tomer asked about this, let me just mention that. So this was like this very effective K-theory spectrum, which is like connective in Motivic sense. But if you want to get actual K-theory, you can also do this thing. Just so put vect or find flat and just periodize with respect to both. So and this works over any base. K-theory is safe. Everything is safe. So okay. So myself, I'm very happy with this picture because let me maybe mention some benefits. So like, oh, I had a epigraph for this story because I heard the other day. So I'm currently in Russia. It's snowing, and I heard the other day one of our ministers saying in her speech that surprisingly, the spread of the virus in Russia does not follow a single mathematical model which existed in the world before. So clearly we need new models. And okay, so benefits of new models for cohomology theories, which is like right, left row. How's it? Okay, like is that so? Okay, I will repeat it because I like them. So they're geometric. They're all frame suspension spectra on some explicit moduli stacks of schemes. So all the maps I wrote are some kinds of forgetful maps. So like clear connections between cohomology theories induced by forgetful maps. Okay, and for example, so the fact that these maps are so natural gives you for free that all these maps are maps of infinity rings, not just some spectra. So in particular, all these maps are infinity ring maps because so like to be an infinity ring for a frame suspension spectrum, it's enough to be a spectrum on some monoid in the Cartesian monadal structure on the in this like category of frame correspondences. So it's like the box product of vector bundles, I think. And so so all these moduli stacks satisfy this, and the forgetful map clearly is compatible with the structure. So they are like infinity ring maps for free. And in particular, so classically in topology, it may be, as far as I remember, non-trivial or in Motivic settings to make the canonical orientation of K-theory an infinity ring map, and here you just get it for free. AG canonical orientation for K-theory, or like for KGL. Okay, and how much time do I have? Oh, okay. Another nice benefit of the new constructions is that you can think of this frame suspension spectra on some moduli stacks as the universal, well, in some sense, universal cohomology theories with this kind of transfers. So universality with respect to certain transfers. But maybe you shouldn't, so like this is an encouragement to action rather than a very precise statement. So for example, so the top equivalence between the sphere and the left-hand side tells you, can be interpreted as like the Motivic sphere is the universal generalized cohomology theory with frame transfers. Okay, this we discussed before. But then the next row is offering to read it as algebraic cobordism is the universal generalized cohomology theory with finite symptomic transfer. So like push forwards along finite symptomic maps. And this is actually, okay, this I can formulate precisely. So that's another theorem, which I just want to mention briefly. So MG, so yeah.
Okay, there is a question asking what happens if you allow all finite maps in your transfers, in particular, not only finite flat, just finite maps, and whether you recover HZ from this procedure.
Or HZ, so I mean, no, I don't think so, because so Motivic cohomology is the universal thing with finite transfers in the sense of Vygotsky. Yes, in that sense, if there is a finite transfers of Vygotsky, then yes. If you just take all finite maps in the world, I doubt that. Well, yeah,
if the asker isn't satisfied, he'll let us know, hopefully.
Okay, so so I was just telling you that algebraic cobordism is the universal cohomology theory with finite symptomic transfers in a precise sense. So this precise sense is that modules over MGL are the same as like generalized cohomology theories with coherent finite symptomic transfers. Overs. Okay, so something you would denote as SH finite symptomic, where you take like the spans, but like this is much easier. You just take the left leg to be finite symptomic and no extra data of any trivialization whatsoever. And okay, so this is okay. This is not how it historically appeared, but morally, this picture suggests you to get this kind of universality statements. And we would like also to tell you that like this very effective K-theory spectrum is the universal generalized cohomology theory with finite flat transfers. We almost told you this, but then Tom found a gap in our proof. So we don't tell you this anymore, but we expect this to be true. So expectation, for example, is that like a similar universality statement, at least in some generality, should hopefully be true for K-theory or stuff like that. So this, my main point is that this picture, let me show it to you last time, gives you a lot of new things to think about. If you work with this kind of cohomology theories, it's like a lot of new information, and maybe hopefully some questions about these cohomology theories which were open before could be attacked with this kind of things. I advertise it. It's please don't ask if we did any computations using this. Because no, not really, not yet. But we hope that some computations could later.
We got a question that's not about computations.
Yes, thank you.
By Nanjung Yang asking, what about Milnor-Witt transfers, which I think you were going to talk
so
about.
let me just say a remark, actually. So there is all these cohomology theories, except for the sphere, which I wrote up until now, were oriented in the sense that they didn't need the help of the trivialization. But there is a similar story if you do non-oriented, not so much oriented cohomology theories, which is so the analog would be to look at the like SL oriented algebraic cobordism and Hermitian K theory, very effective thing. And you know what? Let me do field. Okay, and then the analog of the Motivic cohomology would be Milnor-Witt Motivic cohomology. So let me take characteristic node 2. Okay, so this is, okay, let me introduce you my heroes. So this is like SL-oriented algebraic cobordism. This is very effective Hermitian K theory. And Milnor-Witt Motivic cohomology, which, so the last two are about like plugging in the data of quadratic forms into the considered before cohomology theories, which is funny because like the sphere has quadratic forms inside it by default. So it's, yeah, MSL. MSL is just the universal SL-oriented cohomology theory. So there is an analogous description. So this guy will be frame suspension spectrum on finite symptomic maps with trivialization of, so I write oriented. This is like trivialization of the determinant of the cotangent complex. So like trivialize canonical sheaf. So this would be like if F was a map from Z to X. Then you ask for the data of the trivialization of the canonical sheaf in Picard. Okay, and which means that like MSL has less transfers than MGL. And this dude will be what Tomer asks about. So this would be the frame suspension spectrum on the stack of vector bundles with extra data of a symmetric non-degenerate bilinear form. And this dude will be frame suspension spectrum on the unramified sheaf of Grothendieck-Witt theory. And then there are also forgetful maps. But I wish I left some space here because, let me try. So because this also factors through something which would be replacement of the frame suspension spectrum on the moduli stack of finite flat schemes. And this something is what hopefully Denis is going to tell you about in the next talks. Denis takes care of this. So
you can say the name, I guess, at this point. I don't know.
What?
You can say the name of the algebras.
Oh, sure. I just don't want to define them. So no. Okay. So there will be some kind of finite Cornish standard. Okay. So I hope you are convinced by now that this is a very nice picture. And are there more questions? Oh, okay. I wanted to, so I will tell you in the end about like one more application of the story. But before that, let me give you, do I want this? One sec. Okay, so yeah, so a quick recipe. No, let me just tell you in words. Let's see. Quick recipe to fill in the table. Is so there are mainly two different steps, which I want to explain, like why are there different surnames in the right hand side? If maybe it could all be done by one general result, but that's not quite true. So there are two steps. First is the general result, which is so use Motivic recognition principle. Due to us, which tells you that over perfect field, which is something that Denis already explained to Tomer. So, so over perfect field, so you would have like group-like Motivic spaces with framed transfers. Over K. Embed fully faithfully via the frame suspension spectrum functor into the stable category. And okay, so the image here is the subcategory of very effective spectra. And so this implies that if you have a very effective spectrum, and actually all the things in the table that I put, except for like this big KGL, were very effective, so I could use this. So this means that for any very effective guy, I would have that in the frame settings, it's just the frame suspension spectrum on its infinite loop space. Okay, so that's the general thing, general machinery you can apply. But then in each special case, you need to compute the infinite loop space as something good. So this was like the first step is like this general principle, but the nevertheless, like you need to compute infinite loop space let's say as a with frame transfers in separately for each E. And this, okay, so if you look back to the table, this becomes, so this is easy at the bottom of the table and then gets harder when you go up the table. So if you look at the bottom line, the Motivic cohomology is something whose infinite loop space is clearly Z. So that's like, it's like Motivic and McLean spectrum. So that's by construction. And so Marc's input was to generalize it to arbitrary base, because a priori you would have it only over a perfect field. And then like a bit above, you know that like infinite loop space of K-theory is like group completion of vector bundles because it's K-theory space. And then, okay, you could put here group completion, but you don't really need it. So like it's so clear why you get vector bundles. And then it gets harder, and like that's where this part of the work increases. So it's not obvious at all that infinite loop space of algebraic cobordism is group completion of the stack of finite atomic schemes. That's like additional computation. Okay, so that's what I would like to say about how to get new inputs in the table. And let me tell in the last, in the remaining time about like the last application. So, because there were benefits, and okay, so last application is that we get, well, in particular, we get geometric models for infinite loop spaces. And okay, so I have something like 7 minutes left. This is, I'll say something briefly, and this is just a motivation to Denis' talk, where he will hopefully tell you more details, and also he will tell you some proofs, so you'll be maybe happier. Okay, so let's say we are over a field in this last part, and okay, so say now we are playing the game back, so we have this framed suspension spectrum, and we want to say something new about its infinite loop space. So, okay, so we have that from, okay, let's say from recognition principle, you do know that, well, at least if K is perfect, that infinite loop space of a frame suspension spectrum on like this kinds of moduli stack will be Motivic equivalent to just group completion of this well, pre-sheaf of infinity space. So like object-wise group completion of pre-sheaf of infinity spaces. Where, okay, A was some Motivic space with frame transfer, so it must be like that. And okay, so I want to use this to say something new about infinite loop spaces, although we started with like computing them. So this is, well, an example which I want to consider is like, let's take algebraic cobordism and algebraic K-theory. So we had this canonical map. So, or like you can put small letters here, it doesn't matter because I only care about loop spaces right now. And by what I said, they will be from the table. We get that these are just so typically equivalent to group completions of the stacks of finite symptomic schemes and vector bundles. So these equivalences are like from the table plus recognition principle. And okay, so in the table, I told you that K-theory spectrum also had a different presentation where I would put here finite flat. And it turned out, and that's what Denis might tell you about, that the right-hand side is so here there is an Motivic equivalence. So this is this result. Okay, but these are, okay, so these are some models, but they're still quite abstract. These are some group completions. And okay, the fun part, the last point I'd like to make, that they actually have a much more explicit presentation, at least in Motivic settings. So right-hand side, so this dude is motivically equivalent to just Z times the telescope on vector bundles, where you add trivial vector bundle. And so is this guy. So telescope and finite flat guys. Maybe I should, so okay, in this table, sorry, equivalence everywhere stands for Motivic equivalence. Okay, and the statement is that, well, okay, so this is actually an equivalence, which is the same result. So, and what about finite symptomic people? Well, there we almost know this. We know this up to plus construction. That this is a Motivic equivalence up to plus construction, and this is joined with Tom. Okay, and the last minute, which I have to intrigue you, is that, okay, so we have this, okay, so now we have this model via telescopes and the forgetful map, but these guys have even more, well, from some sense, even more geometric models, as in they're okay, like, represented by some int schemes, and these are the Hilbert schemes. So these guys are again Motivic equivalent, A1 equivalent to well, some telescopes now considered in the world of Hilbert schemes. So this is something Denis will introduce you to. So this is Hilbert scheme of infinite defined space where I stabilize with respect to degree. And this is its same thing where I take points which are local complete intersections. And this is just the open embedding. So we get a Hilbert scheme model for both algebraic cobordism and K-theory, and the connection between them is just the open embedding of a Hilbert scheme of points which are local complete intersections, so defined by the right amount of equation among all points. So that's the end of the story. Thank you for your attention, and please ask more questions.
マジダメだこのゲーム。
環境が
マジで本当そうだよ。
本気でやるのがアホらしい。
アホらしくなるこの。
なんかもう上を目指すっていう考えはあんまりない。
Denis, I think you should unmute yourself.
I should. Okay, so if you have any questions, raise your hands or write them. I see that Tomer already has another question. So Tomer, go ahead.
So here's my question. So is it maybe possible, I don't know, maybe that's, but to do something like take, instead of vector bundles, something like some category of modules over the category of perfect complexes, some kind of a categorification of that to get a higher height Motivic cohomology theory? Something that is kind of K of K in some sense. Is that that, I don't know, something like that possible? You're muted.
Oh.
I unmuted you. Go ahead.
Thank you. Yeah, Tamara, that's a good question, and I don't know right away an answer. That's certainly something you can try doing. I don't know how to succeed.
Would this be like the analog of the two vector bundles of Ausonian Rogness, right? Yes.
I think, yeah, some, you know, I don't know the Ausonian Rogness construction, but right, there's this, you can do like two, you know, you can take like modules with categories which are modules, stable categories which are modules over the category of perfect complexes, and kind of, you know, they classify them, and that's you know, that in some sense produces for you kind of some form of K-theory of K-theory in some context. I don't know if this thing can be made into in a good way into a functory on this category, and if it does, what would happen? But I was just wondering, because it's kind of, it's tempting to, there's a lot of space between KGL and MGL, right? That's kind of the,
yeah, we've been staring at this space for a while. Personally, I didn't try what you suggested, so maybe if you discuss this later in more detail, I would try to make this work.
Great, thanks.
Okay. Okay. Are there any other questions? Well, if there are no other questions, I'm going to unmute you, everyone. And oh wait, no, there is a question. A question appeared. So is fsyn still a symptomic site? I'm not sure I follow the question. So
okay, fsyn is the following thing. You take the stack of finite symptomic schemes, and there you have an so okay, maybe we should ignore the Z part, and then just take on the stack of finite symptomic schemes, consider the map which increases a degree by 1 by adding, like by taking this joint union with the trivial cover, and then take colimit along this map, and you get something. So this colimit is like this telescope is what computes the group completion up to Motivic equivalence. So it's not. Oh, maybe I should stop sharing the screen, or not stop. But yeah, it's not. This story was not about changing sites. I think so. In Marc's talk, Marc considered different kinds of sites, like Nisnevich topology, CDH topology. Here, I didn't do any of that. It was all like in the Nisnevich sites.
okay. Let's see if there are any other questions. Doesn't seem like it. Okay, so I'm going to unmute everyone to thank the speaker again. So. Now I'm going to, well, I'm going to leave everyone, no. Okay, I'm going to do the breaking room things again. Let me mute everyone first. So we are 44 people. Can you try it?
Did you stop recording, or did you record it too?
Thank you.
Okay.